Hello everyone. Welcome to the live solve we're gonna do today. It's a pleasure getting to teach all of you guys, and hopefully you can do some cool and exciting math. So with me is my partner Owen, and he's actually really good at math and really impressive. Um, and so a couple of things about himself. Obviously, he's done math competitions for a while now, and let's see. And he's actually really strong at math. In fact, he has sorry, one sec. I pulled this up, but I can't find where it is. Oh yeah, so he's a USA JMO qualifier, and he has made Amy 5 times, and he's done a lot of other cool things, such as doing like curriculum development at Mustang Math and a lot of stuff. So he's really impressive, and hopefully you guys can learn a lot from him today.
Yeah, hi everyone. I'm excited to be here today as well.
Yeah, awesome. Do you want to get started with problem number one, Owen?
Sure. Okay, so problem number one. Today we're covering the Math League. So this is sprint round number two from this test. And the problem is up here. So Andy sorts 200 tomatoes and finds that 15% of them are rotten. He places all the tomatoes that are not rotten into containers that can each hold up to 6 tomatoes. What is the smallest number of containers that Andy needs? All right. So we first probably want to find, the number of tomatoes that are not rotten. So like this quantity over here. And that would be 200 times 85%, since 15% of them are rotten. So if you carry out this calculation, you should get 170 tomatoes. All right, and now we got to fit these 170 not rotten tomatoes into containers of 6. So each of them is going to be able to fit 6 tomatoes like this. And to do this, one thing that seems like it would work is to divide 170 by 6, right? So if we try to divide 170 by 6, we can do some division. We put a 2 here, subtract 120, and we get 50. So we get somewhere in between 28 and 29. So which one of these numbers should we choose to be correct since the answer is not an integer? Do you have any ideas, Kevin?
Yeah, so basically we want to see, so basically we want to like figure out which one, sorry, my screen is a little blurry. So we want to figure out which one, is non-integer, and also, going a bit back to the problem, we also want to figure out what the smallest number of containers Andy needs, right? So I guess one way to tackle this is going to be, whoops. So one way we can actually tackle this problem is by looking at this. So we figure out what the remainder is. We know that we want all the tomatoes that aren't rotten. We know that 15% of them are rotten. So 85% of them are not rotten, which 85% of 200 is going to be 170. And as we've already divided that by number by 6, after dividing by 6, we will get 28.33333 and so on and so forth. So we'll have 28 containers that are fully filled with 6 tomatoes in the ideal circumstance. And we'll have 2 tomatoes remaining that we need to put in a separate container. So the smallest number of containers we need is just 28 plus 1, which is 29. And
Right.
let's see your answer. Yeah, that's correct.
Yeah. So it'd be very tempting to put 28 because of the word smallest, but remember that we still have 2 tomatoes left that we need to fit into a container. So we're going to need 29 as our smallest here.
Yeah, absolutely. And I can move on to the next question, which says two positive whole numbers greater than 1 and multiplied to 576 and have no common factors other than 1. So what are the sum of those two numbers? Well, to start with, we can prime factorize 576, and we can factorize this as, well, if you know your perfect squares a lot, then you know that it's equal to 24 squared. But I guess the more natural way to do this is we can say that 576 divide, obviously this is a multiple of 4 because the last two digits is a multiple of 4, so after we divide by 4, we get 144. This also is a multiple of 4, so we can still divide by 4 to get 36, and 36 is just 4 times 9. So we have 4 times 4 times 4 times 9, which equals 2 to the 6 times 3 squared. That's a prime factorization. And now we can see that if we want, two positive whole numbers to multiply to this thing, but have no common factors, well, then one of the numbers just has to be 2 to the 6th, and one of the numbers has to be 3 squared. So then our two numbers would sum to 64 plus 9, which equals 73. And let's check if our answer is correct. And indeed it is.
All right, this means we can move to the next problem, which is about Aiden and his ball course. So Aiden's ball course is composed of two concentric semicircular arcs of radii 7 and 10 that are cut off by collinear line segments as shown below. In addition, the course has a circular hole that is just large enough to fit a spherical ball with a volume 4 3 pi. Interesting. I think that's a 4/3 pi, but I'm not sure.
Yeah, I think it might be 4/3 pi. We can go with 4/3 pi, I guess.
Yeah, let's go with 4/3 pi. Okay, so we now have this 4/3 pi as the radius of this ball, and this is not a great picture because it says that this circular hole is, just large enough to fit a spherical ball. Oh, yeah, so this circular hole is going to have we need to find the radius of this circular hole. And to do that, you might find it helpful to know the formula of a sphere. And the formula for the volume of a sphere is actually just 4/3 pi r cubed, which means that this sphere has radius 1. So this sphere has radius 1, right? And now we want to find the area of this ball course excluding the hole. So we need to remember to just subtract this area at the end. But otherwise, we can kind of take these two circles, right? We have one half circle of radius 10, and we want to subtract this inner part, which I'll shade in green, which is the semicircle of radius 7. So to do that, we can use the area of a circle formula, which is pi r squared. So we should take pi times 10 squared, which is the outer circle, and subtract that by pi times 7 squared, which is the inner circle, and then divide by 2 because we remember that these are semicircles. So we should get something like 51 over 2 pi. However, we have to remember to subtract the area of this circle because it says we want to exclude the hole. And the hole has a radius of 1, so we can find that the area of this circle is just pi. Therefore, we just subtract pi to get a final answer of 49 over 2 for A, since it only wants the coefficient of pi. And let's check our answer here. And it is correct.
Yeah, and that's a great job. Now we can move on to the next question, which says, three consecutive positive whole numbers have the property that the smallest number is a multiple of 6, middle number is a multiple of 7, and the largest number is a multiple of 8. So if we write this in algebraic terms, let's say the numbers are going to be like x minus 1, x, and then x plus 1. So these are the three consecutive whole numbers. So that means that the smallest number is a multiple of 6. So x minus 1, so 6 divides x minus 1, 7 divides x, and then 8 divides x plus 1. I want the second smallest possible median. So one thing we can notice here is that using a bit of modular arithmetic, if you guys know what that is, we can say that x is congruent to 1 mod 6 based on the first condition because the remainder when x is divided by 6 is equivalent or equal to the remainder when 1 is divided by 6. That is essentially what modular arithmetic is. So it's just a bit of fancy notation, but also we can say, x is congruent to 0 mod 7, and then x is congruent to -1 mod 8. Great. Now we're going to do a bit of manipulation over here, and we know that x is going to be congruent to 1 modulo 6, which means that x and 1 have the same remainder when divided by 6. However, 1 and 7 also have the same remainder when divided by 6, so this is also congruent to 7 modulo 6. Similarly, this one is x is congruent to 0 mod 7, is also congruent to 7 mod 7 because they both have the same remainder when divided by 7. And similarly, this is also congruent to 7 modulo 8. So we know that x is going to be congruent to, or x is going to have a remainder of 7, or, I guess possibly less than 7, when divided by both 6, 7, and 8, or it's going to be congruent, which means that we know that x minus 7 has to be divisible by 6, 7, and 8. So essentially, this also means that x minus 7 has to be divisible by the least common multiple of 6, 7, and 8. And this least common multiple, well, the value of the least common multiple of 6, 7, and 8 is just going to be 7 times 24 equals 168. So then we know the smallest possible value of x is going to be 7. So the second smallest possible value of x is going to be 168 plus 7. And this is going to be equal to 175, which is our answer. And here we just use some modular arithmetic to make the problem simpler, but the main idea is, after setting up this, we just know that 6, 7, and 8 both have to divide x minus 7. And indeed, 175 is the correct answer.
All right, great. This means we can move on to the next problem, which is about two six-sided dice. And these two six-sided dice are initially blank on all 6 faces. A total of 6 dots are painted on the 12 faces of the dice, with each face having 0 or 1 dot. Assuming each face is equally likely to have a dot, what is the probability that at least one of the 2 dice have a dot on its top face? All right, so one of the ways to do this is to use this thing called complementary counting, where instead of counting the probability that at least one of the dice has a dot on its top face, we count the probability that neither of these dice have a dot on its top face, and then we subtract that from 1 because probabilities have to add up to 1, right? So another important thing to note here is that there are a total of 6 dots. So we are essentially choosing 6 of these faces to put the 12 dots on. I'm just going to draw the 2 dice here really quick for visualization. All right. And so we're essentially choosing 6 of these sides to not have anything blank on, to not have any dots on them. So the number of ways to choose this such that 2 of the dice, are these 2 top faces is 10 choose 4. Because by establishing that these on the top are blank, we have 4 more sides that we want to make blank, which is 10 choose 4 ways to do it. However, overall, there are 12 choose 6 ways to choose the sides that are blank. So the probability that both of these top sides are blank is this probability, where we divide this 10 choose 4 by this 12 choose 6. So we take this 10, and if you know how to evaluate these choose functions, becomes very easy to do. So we can write it like this: 10 times all the way up to 7, and then 4 times 3 times 2 times 1, over 12 times 11 times 10 times 9 times 8 times 7 over 6 times 5 all the way to 1. And let's just make this a little bit easier. And I'm going to use a calculator to do this. So we can also cancel out these fractions by hand, but okay. So if we cancel this out, we should get this 2 and this 4 cancel the 8, the 9 and the 3 cancel, so we have 210 on the top. And our bottom, this fraction right here, this is 720, so that should cancel with this, and we have another 6 left. So this should be 3 times 7 times 11 times 4. And now we can cancel this out, have this 10, and we should get 5 over 22. This seems very interesting, but we're not done yet because we have to subtract this from 1 to get the probability that at least one of the 2 dice has a dot, because we counted the probability that neither of them do. So our answer should be 17 out of 22. I'm actually not too sure about that, so let's check the answer. It is correct. All right, so that was a bit of a long one, but we made it. Someone says, how did we get 10 choose 4? Right. So what I was doing here is I'm counting the probability that neither of these 2 dice has a dot on its top face, right? So we're kind of setting these as, blank faces. Let me just write a B as a blank face. And we know there are 6 blank faces in total. So by making these blank, we have 4 other faces that are blank. So we're choosing 4 more from the 10 remaining faces that are blank, which is how we got this 10 choose 4. Does that make sense? All
Yeah.
right, great.
Yeah, that's great. Now we can move on to the other target round number 5, which is the smallest whole number that is 4 less than a perfect square and 5 greater than a positive multiple of 3. So this part is interesting, 5 greater than a possible multiple of 3. So this means that we can write this whole number as 3k plus 5, because it's 5 greater than the multiple of 3, and k is going to be some integer. And then it's 4 less than a perfect square, so if you add 4 to this number, this is going to be a perfect square, which means that 3 times k plus 3 is going to be a perfect square. Let's say a squared. So the first thing we can notice here is that a is going to be a multiple of 3 because we have a factor of 3 here, right? So then if we say a is equal to 3b, well then this is going to be equal to 9b squared equals 3k, or 3 times k plus 3. In other words, we have k plus 3 is equal to 3b squared. And now we just want the smallest whole number, so the smallest possible value of k. And now to test smallest possible values of k, we can sort of first look at values of b, right? For instance, we know that if b is 1, then k is 0. So if b is 1, am I making a mistake here? Just to check. Oh yeah, so if k is 1, b is 0. Or if b is 1, k is 0. But then if k is 0, then 3k would not be a possible multiple of 3. So instead, we must check b equals 2. If b equals 2, then k is going to be equal to 12 minus 3, which equals 9. And then 9 does work because 3 times 9, which is 27, is a possible multiple, positive multiple of 3. So in going back, we want 3k plus 5, or 3 times 9 plus 5, which is 27 plus 5, or 32.
All right, nice. Looks like that one worked out. Let's pull up the next problem. All right. So how many ways are there to order the first 7 positive whole numbers such that the positive difference between any two consecutive numbers is odd? Okay, one thing that we should start out by doing is, we have 7 blanks, and what does it mean for the difference between any two consecutive numbers to be odd? If you do a little bit of testing, you realize that saying this is the same as saying that the numbers must alternate between odd and even. If we have two even numbers, the difference is always going to be even. And if we have two odd numbers, the difference is always going to be even. So we need to alternate odd, even, odd, even. All right, so let's write out the numbers. 1, 2, 3, 4, 5, 6, 7. Notice that there's 4 odd numbers and 3 even numbers here. So we're going to have to alternate like this. Odd, even, odd, even, odd, even, odd. And now notice that it doesn't actually matter what numbers we put in these slots as long as they are odd and even as we want them to be. So we can rearrange the odd numbers in any way we would like, which is 4 factorial. And then we may rearrange the even numbers in any way we like, which is 3 factorial. So this gives us 24 times 6, which is 144 as our answer. And let's check if this is correct. And it is.
Yeah, that was amazing. Let's see. Now we can move on. Shoot, I'm losing track. Now we can move on to this question, which says the ratio of the measures of two supplementary angles is 5 to 7. So what's the difference between the measures of the two angles in degrees? So the way we want to do this problem is, again, we want to define variables. So the first variable is going to be the two angles, right? So one angle is going to be 5x and one angle is going to be 7x. However, they are supplementary, so they must sum to 12x, which is equal to 180 because they are supplementary, which means that x is going to be 180 over 15, or 180 over 12, which is 15. Now, the difference is going to be 75 and 105. So the difference is going to be the difference between these two numbers, which is going to be 30, which is our final answer.
All right, that was terrific. Let's do this problem. So, wait, sorry, give me a second. Yeah, let's do this problem about Ivy walking her brother Griff home. So this is a bit of a long one, so we're gonna have to read a bit carefully. So Ivy is walking with her brother Griff from home to school at a constant speed. Okay, this might be important. At the speed they can make the trip in 15 minutes. Okay, so home to school is 15 minutes. We don't know how long it is, but it's 15 minutes. So at some point during the walk, Ivy realizes that she forgot her homework. So she jogs back home twice as quickly as she walks, and then sprints to school 3 times as quickly as she walks. While Ivy gets her homework, Griff continues walking to school, and they arrive at school at the same time. How many minutes after leaving home did Ivy realize that she forgot her homework? So one thing that we're going to do here is we're going to measure distance in terms of time because Ivy and her brother Griff walk at the same speed and their speed doesn't change except when Ivy starts running. So they're walking along from this H to this S. Let's say they've gone X minutes before Ivy turns back. And this part is 15 minus X, right? So Griff takes 15 minutes to walk to school. That's a given. And we know Ivy takes the same amount. And how long does Ivy take? So Ivy first covers this X minutes distance of walking, right? That takes her X minutes. Now she turns around and jogs home. And that's not going to take her X minutes anymore. It's going to take her X over 2 minutes because she's going twice as fast. Finally, she's going to sprint this 15 minutes worth of walking, but that 15 minutes worth of walking is going to be 5 minutes for her since she sprints 3 times as quickly as she walks. So we have this nice little equation here, and this becomes 3x over 2 equals 10, from which we can get that x equals 20 over 3, and that's exactly what we wanted since x is the amount of minutes that she spends walking before she realizes that she forgot her homework, and 20 over 3 should be our answer. Let's go check that real quick, and yes, we got it correct.
Awesome. Now we can, okay, hopefully I haven't, now we can move on to this question, which says that suppose x and y are positive numbers such that xy equals x plus 2, and then 5x equals y minus 4. And we want to find x. So this problem is interesting because one thing we can note here is that xy equals x plus 2 means that if we, and then 5x equals y minus 4. So the second equation tells us that y is going to be 5x plus 4. So then we know that x times 5x plus 4 is equal to x plus 2. This means that 5x squared plus 4x equals x plus 2, which says that 5x squared plus 3x minus 2 equals 0. And now we can just use the quadratic formula here. The quadratic formula says that x is going to be negative 3 plus or minus, let's see, b squared, which is 9, minus 2ac, 4ac. 4 times 2 times 5 is going to be negative, so it's going to be minus negative 40, which is plus 40, all over 2a, which is 10. This gives us, okay, I disconnected for a second, all good. Negative 3 plus or minus 7 over 10. Now we want the positive value of x, so we have to take the plus sign here. It's going to be negative 3 plus 7 over 10, or 4 over 10, which is going to be 2 over 5. And indeed, 2 over 5 is the correct answer. Great.
All right, that was terrific. So let me pull up the next problem. Okay, so our next problem is 72 people are seated in a room with chairs arranged in a 5 by 15 rectangular grid. The unoccupied chairs, so let's make a quick note here. There are 3 unoccupied chairs. They are decorated with flowers, and no 2 unoccupied chairs can be in the same row or column. So no 2 unoccupied chairs can be in the same row or column. How many ways can the decorated chairs be located in the grid? So the decorated chairs is the same as saying an unoccupied chair, since the unoccupied chairs are decorated. So essentially, we just have this. I'm not going to draw it all out, but we have 15 rows of this. And essentially, we want to choose 3 of these seats so that none of them are in the same row or column. And one of the things we can realize is that it doesn't really actually matter what we choose as our first seat because it's going to eliminate 1 row and 1 column. No matter where we put it, it's going to eliminate the same amount of things. So let's just put it in the upper left corner for simplicity. But we can put it anywhere in the grid, right? So that's 75 choices already. And our next one, we have now eliminated 1 row and 1 column. So the number of seats remaining is going to be 4 times 14, regardless of what seat we chose. So that's 56. And, let's just choose this seat for simplicity again. All of these seats are now eliminated. And finally, we have 3 times 13 seats remaining, regardless of what we chose, since we've eliminated 2 rows and 2 columns by now. So that gives us 39. And I'm not quite sure how they expect us to do the multiplication in a contest, but let me do the multiplication with a calculator. So 75 times 56 times 39. Uh-oh. Yes, 75 times 56 times 39, you end up with this very large number, 163,800. 163,800. But we're actually not done yet. So if you are paying very close attention, you might realize that the problem only asks for how many ways can the decorated chairs be located. So there's no distinguishment between the chairs, which means that we need to divide this by 3 factorial or 6 to prevent overcounting. So we now must do long division again and divide this by 6 to get a final answer of 27,300. And this should now have eliminated all the duplicate ways to choose the chairs. And this is indeed our correct answer. Wonderful.
Yeah, awesome. Let's see. I think I might have skipped a question, but I guess we can go back later. For the sake of time, it's kind of hard to look back. Okay, wait a second. Let's see. Okay, whoops. I realized I should have the answer. We can do this one. So in a grid of 49 unit squares, 3 rectangles that each have area 12 are drawn, as shown below. And how many unit squares are in exactly 2 of the 3 rectangles? So basically for this problem, so we have, 3 rectangles, and then we want to figure out how many have exactly 2. Yeah, so I guess we can sketch this out for a second, right? But it was important to be really careful here. So this is one of the rectangles. This one is 1, that drawing. So this one's 1, and this one's the other one. So let's first look at the intersection between these two. We have, in these two, but not the third one, we have these 3 squares, where in these two, but not the third one. This obviously is squares, it's going to be in the third one, so it's no go. Now we can look at this rectangle, the bottom left one, and the top one. These 2 rectangles share 1 square that's not within the other one. And then finally, this rectangle, the top one and the right one, share 3 squares that's not in the left rectangle. So in total, we have 3 plus 1 plus 3, which is going to be equal to 7, which is our correct answer.
All right, fabulous, and great job to everyone who said 7 in the chat. That is correct. So our next problem is about Evan has some number of buckets, and 60% of the buckets are occupied. Only when Evan fills 3 more buckets will at least 70% of the buckets be occupied. If Evan then doubles the total number of buckets, what is the greatest possible number of buckets that Evan will have as a result? All right, so this doubling part doesn't really matter to us now, because if we just figure out what the greatest number he has before, then doubling that is obviously going to produce the greatest answer possible. So he has some number of buckets, and exactly 60% of them are occupied. So let's say he has X buckets, then we know 3/5 or 60% of them are occupied, which is 3/5 X. However, we know that when he fills 3 more buckets, at least 70% of the buckets are now occupied. So we can write this as 3 over 5x plus 3 over x is more than 7 over 10, or greater than or equal to, I guess. And if anyone knows the cross multiplication trick, it's that we can just turn this into 6x plus 30 is larger than or equal to 7x, which means that x is less than or equal to 30. So the largest we're going to be able to make x is 30. And you can check that if we have 30 buckets, this works. It actually happens to be exactly 70%. So we want 30 buckets at the beginning, which means that at the end, Evan is going to be able to have 60 buckets. All right. This answer is correct. So yeah, the doubling part was a little bit irrelevant there. You just needed to not forget it at the end. And yeah, great job for everyone who said 60 in the chat.
Yeah, awesome. Let's see. I don't think this problem has been done before, right? Owen, could you check?
We covered that problem. Yeah,
Oh
we
shoot,
went
yeah.
through it.
Okay, I didn't write anything on it, so it might have been out of. I think a lot of my stuff is out of order. Is this
Yeah,
problem? I don't think this problem has been done for, right?
I covered that problem too.
Okay, wait. Oh, I think I see where it ends now.
Yeah, I think we're a bit out of order with each other.
Yeah, okay, that makes a lot of sense. Yeah.
I actually think we have like one problem left.
Okay, well, we can do the last problem then, I guess. Okay, so the ping time is the average
Yeah.
time data takes to go from the client to the server and back. Eli recorded how long it takes to process 5 inputs for an online game in the table below, and how many milliseconds is the ping time across the 5 outputs. So it's the average time data takes to go from the client to the server and back. So we want to add these two for the total ping time. So adding this is going to be 107. This one is going to be, let's see, 96. This one is going to be 78. This one is going to be 100, and this one is going to be 119. So we just want to take the average of them to get the total ping time. Let's see. So 107 plus 96, that's going to be 203 plus 78 is 281 plus 100 is 381 plus 119. 381 plus 119 is going to be 500. All divided by 5 because we want to take the average of the 5 samples. It's going to be 100 milliseconds average ping time. And indeed, 100 is the correct answer. So yeah, great job, everyone.
Yeah, that should be all the problems we have for today. I can do a last check.
Yeah, cool.
Yeah, it doesn't seem like we had, I think we covered all the problems we had for today.
All right, awesome. Yeah, that was really quick. I mean, I think these problems are a bit simpler than our usual live solves, but thanks for joining us today. And please check out live.poshenload.com and if you like today's session, please feel free to contact us at any time. It was really great teaching you guys, a really fun problem today, and thank you, Owen, for showing up and coming. I believe that'll be it. Bye, everyone, and have a stupendous Sunday.
Yeah, thanks for coming, everyone. Hopefully that was a fun, fast-paced session for everyone as well. I certainly had fun.
Yeah, me too. Bye bye, guys.
All right, bye-bye.